a former CTO and VP, and I love startups. Did you know that AWS, there's an entire org just dedicated to startups? And we've been in your seats. We're ex-founders, ex-early operators, ex-VCs. There's so many goodies to get your hands on. I can't even get to all of them today. If you want to learn more, a great place to start is to contact your account manager or visit the Activate console. Today, I'm going to talk to you about my experiences as a CTO building ML-ready engineering teams and using services to set expectations and bridge the gap as you're building your team. One of the top questions I'm always asked is the best way to hire ML engineers. Now, you could attend every ML conference, but the truth is that the need far outweighs the supply when it comes to talent in AI specialists and data science. The best organizations aren't just hiring MLEs, they're training them. They make a culture to address common skill gaps and use state-of-the-art frameworks and practices. If you're a startup, you know everyone has to wear multiple hats. You may not be able to take the 3+ years to learn every machine learning technique possible, but it is possible to understand all the roles and responsibilities of an ML team without a PhD. ML teams can be composed of people with many different skill sets. On the research side of the house, I've seen everything from a data analyst to a postdoc ML researcher. Right away, people ask me, are researchers software engineers? And there are arguments to be made on both directions, but for my teams, researchers were included in engineering. And they learned to adapt standard software engineering practices like 100% code review, writing unit tests, and codifying data schemas. Many existing software engineering practices apply directly to ML systems, but are simply not taught in university or widely used in research. Other practices like how to monitor a production system will have to be adapted and extended to deal with ML components. Other roles exist in a lot of software organizations like data engineers and operations engineers. But in an ML team, each member is familiar with how to build, train, and deploy a machine learning model. It's amazing how predictable the problems when building an ML team will end up and how easily they happen. Researchers may not have any training with deploying a model or understanding the system infrastructure it will use. They might not have any context on the machines used and how they might impact performance. A MLE might find themselves translating a model from R to Python or optimizing a model in C++ to run on specific hardware. It might be much easier to rewrite from scratch than adapt existing code. Data engineers frequently discover the data used to train the model is different from the data used in production. Inevitably, they end up maintaining a lot of glue code. Operations can feel like a brave new world. If you're lucky enough to have an SRE team, as you scale your solution globally, they may discover that a model deployed regionally drops in accuracy as it is no longer uniformly distributed. Now let's say for a moment you decide to go ahead and build a team. Your startup has an amazing mission statement, you attend some of the top ML conferences, and you hire a fantastic data scientist, particle physicist, PhD. I can tell you, I often hear the same things. Like, don't worry, the data is ready. It's in the production DB replica. ML projects will frequently combine a lot of different types of data types in one project. You might have structured data like what's in your production Postgres, with unstructured data like images and video, semi-structured data like sensors or JSON, and important metadata to keep everything clean. Now, if your data is in a read replica of a production DB, you need to figure out your data story before you hire your first data scientist. Not only is your team going to be working with a lot of different data, but they need a safe place to do so without violating production rules or compliance rules. I've personally had to purchase large data sets to get started. I've even paid actors to make training data. If that's you, a good place to start might be the Registry of Open Data on AWS or the AWS Data Exchange. Now, depending on the data maturity of your organization, the starting point for your data might be as simple as loading some data into S3 or pointing your database from a data warehouse like Redshift Spectrum. Early on, I see a lot of companies batching data processes with retraining their model frequently, even daily as these new updates come in. It surprises a lot of engineers when I tell them to have their data on S3 and just spin up compute as needed. But this is the role of the data engineer on your team and can be managed with the help of software services. But the concept is straightforward. You pre-join and pre-calculate all the data on your network storage in order to make it scalable for large-scale batch processing without risking your production system. Now, there are different architectures, and I hope you use the software service instead of inventing your own. But it can help to have a visual idea of what this data might look like. I think of S3 zones and how you can materialize that data into different views and calculate statistics before people and machines look at it. Now, you can imagine a lens where the bulkiest data is analyzed with Athena, and a small amount of that is trained and processed in SageMaker. Storage is pretty affordable, so maybe you have the biggest lens as raw data. It comes straight from the source as is and has an IAM rule that humans can't access it. Your curated data is then cleansed using data quality rules. That same data is materialized into intermediate data sets that tables required for transforms to run. Further, linked data sets that are denormalized and aggregate without any PII. You might archive old AWS experiments in Glacier or export datasets for partners, indexing, and model hosting. Let your BI team take a quick look on QuickSight without violating compliance rules. In this example reference architecture, AWS Glue handles the mapping into S3, and SageMaker provisions the compute. These are the resources that are necessary to build a movie recommendation system. By effectively separating out storage and compute, you only use the resources you need as you need them, saving cost and reducing complexity. You don't actually have to build these steps from scratch, and there are tools that are going to help you stay in the best practices to scale from your pilot all the way to your global architecture. There is an end goal for your data journey. It's called a data lake architecture, where it's safe for researchers to experiment without impacting production or violating any policy, and they can receive data updates in a timely manner. For organizations with very frequent data updates, I would love you to consider AWS Lake Formation or Redshift Lakehouse architecture. They're great places to start. But some factors to consider are how often I'm updating my data, do I have any compliance or governance rules, and always, always be sure to have a plan for privacy and security. Ultimately, your data scientist or researcher wants to work in a collaborative manner to show intermediate results. One of the best skills that your team can have is the ability to run code notebooks for experimentation. You know you're ready for a machine learning researcher role when a new team member can explore and combine data sets in a code notebook without begging for permission. Now, one of my teams once built an inventory model to predict what goods were going to be sold. We were so proud we could confidently say we're going to sell 100 sandwiches, 200 chips, 500 sodas this week. And it wasn't until business operations came and said, oh, that's great, how many turkey sandwiches? We only knew how many sandwiches were going to be sold, not what kind of sandwich. And then we've discovered that the reason ops wanted the model to be built in the first place was to find out how much turkey are we going to have to buy. It is frequently the case that the problem specification will be left to the research team. And in my example, our data scientist was too busy building the data lake to meet with business operations. These kind of mismatches are incredibly common. And generally, mismatches are related to a lack of knowledge of business goals or objectives that the model was going to help satisfy. Amazing research from Grace Lewis from Carnegie Mellon University taught me that in machine learning, a mismatch is due to incorrect assumptions about the development, deployment, and operations of the system. Information that could have been shared between stakeholders would have avoided the problem in the first place. These sorts of miscommunications are deadly. Everyone has experienced delays due to rework, incorrect results, poor system performance. All of these will lead to system or mission failure. No one wants to be on PagerDuty. No one wants a bad result. The easiest way I had to encapsulate this concept is by exploring the word performance. And there are 3 different perspectives I could take. To a researcher, performance is entirely how does the ML model make a prediction from training data, and they don't have any production context. to engineering, probably thinking, how is this going to integrate with my API? And ops are thinking, how is it going to handle the load of the system? As many of you who have read Tech Debt and Machine Learning know, it's uncommon for teams to plan on how to go from the research to the operational phase of a machine learning project. In the machine learning research phase, it's usually a scientific project or proof of concept, and the ML code may be the entire focus. In the ML operations phase, after the POC, bringing your models into production, ML code will become the smallest code in the system. My rule of thumb, any individual component of the system should not be more complicated than what a single engineer can hold in their head. To iterate quickly from prototypes to production, you need to put the right tools and roles and infrastructure in place. This is called the model development lifecycle. But for a startup who may not even have some of these roles in place, I want you to think of it as your journey to machine learning operations, or ML ops for short. Some concrete examples of the mismatch that we see are poor systems performance from selecting the wrong compute, poor model accuracy because the training data has a different distribution from the production data, an absence of model monitoring to detect diminishing model accuracy, often leading to complete system failure in production when there isn't a test for the model in the changing production environment. To avoid these problems on your journey to ML ops, I want you to make explicit as much as you can as soon as you can. It's really helpful to know the kinds of places it can go wrong and to codify it into contracts like a data schema or provisioning your infrastructure with code to automate lifecycle testing and development. It's actually not very different from the development of a regular software system, but in the case of ML, the difference between the data and the model performance we see at training and production is the performance of the system. It falls reasonably into these categories in this slide, but I encourage you to imagine your own system and how you could codify the contracts between these relationships, like retrain your model with data that is derived from production data. Make a schema. Now, if you're starting from scratch, understand it can be a costly and complex process to develop all the components of a machine learning system. But you don't have to start from scratch. You can use existing services like SageMaker to place all of these steps into their best practices while you figure out the details of your own system. The greatest confusion and uncertainty I hear from most of the startups that I work with is that they think they must use every piece of SageMaker end to end. But SageMaker is completely modular. If you're already developed parts of your system, you continue to use your own IP and integrate it as needed. If SageMaker isn't your speed, you can still build with the same steps with open frameworks like Kubeflow. The important takeaway is not to try to define all these steps on your own, but rather start with an end-to-end solution, and then switch out the parts as you think is relevant to your business. If you are brand new and have no background, I recommend you start with SageMaker Jumpstart, available in the AWS console. The solutions can be used out of the box or customized for a specific business problem, eliminating the need to train an ML model and string together different components of the ML application. I know many folks first experimenting with machine learning think that algorithm selection is going to be really difficult, but a good rule of thumb is to skip ML altogether. Just use a heuristic to get started. A heuristic will have some noble accuracy, like 70%, but then with deep learning, I can keep inching it better and better until I get that 98% or better. If not a heuristic, go ahead, pull a pre-built model from the ML marketplace. It's simply not required that you understand the internals of a model to represent each step of the ML system in your ML process. Once you finally deployed end-to-end, you can avoid the common mistakes problems by creating a notion of goodness for the model and monitoring production. Here's what Amazon SageMaker Model Monitor looks like. In this example, view charts with important model features and summary statistics. Watch them over time and compare them with features used in training. Some features drift when the model is running in production, which can indicate that it's time to retrain your model. Now some takeaways. When you're building and scaling your ML team, I want you to have empathy for the different workflows and roles you can expect to have within your team. Whatever the maturity of your organization, be prepared with a data story. Machine learning literally means for a computer to learn from data, and whoever has this role needs a safe place to experiment. Codify assumptions as much as you can. Use software services to follow best practices. Avoid skipping steps or hidden assumptions. And please, 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 fake it till you make it. The internals of any system could be very complicated, but you can avoid surprises by thinking broadly before focusing on any individual component. We have a lot more opportunities for you to learn and accelerate your journey of ML on AWS. You can check out this QR code for more resources, and consider upscaling your team with AWS training and certification. Thank you for attending. I really appreciate your feedback, and I want to know what topics you'd like to hear about. What kind of machine learning team are you hoping to build? Thanks so much.